Swayam Prabha. Digital India. Educated India.
So now let us go for the very first session. So it is on introduction to the advanced manufacturing techniques. So this session will be taken by Professor G.L. Samuel. Yes, sir. Over to you, sir.
Yeah, good morning to all. One more time, we welcome you all for this short-term training program. So you have come from all different places in India. So we thanks for that. So as we have been talking about the plan for this course, so we had the inauguration. So we'll have my session, so followed by Professor Shreyas Melkote's sessions. So we'll go ahead with the first lecture. So what I'm going to do is I'll be giving you an introduction to the various advances in the manufacturing technology. But primarily, we'll also be talking about the facilities, what we have, and the work, what we are doing here at IIT Madras. And during your visits, you can have a look at them. And then even in your spare time, you can go visit those facilities and talk to the research scholars. So that is the aim of this presentation. As we all know, manufacturing is the most important area for the growth of any country. So if the industry in that country is developed, we call that country as a developed country. And also for the economy of a country, so the industry actually will be the backbone of the economy of a country. So we have been looking at the manufacturing from various aspects, and nowadays actually with the introduction of artificial intelligence and combination with the manufacturing technologies, so the developed countries are pursuing the goals which are beyond our imagination. So basically, if you look at the manufacturing, so it has actually derived from two words from Latin which are called manu and factus. Manu means hand, and then factus means made. So manufacturing means literally it is made with hand. But now if you see what is happening, so we are able to actually manufacture the components and even have the whole factory without the intervention of the human beings. So that are the development which has happened over several centuries. And if you go back and then look in the human being history, so we find that people were using the sharp tools even during the Stone Age. So we now know that how when we make sharp things, we'll be able to cut. So the concentration of stress, strain, and then shear strength, all these things we know. But those days, even though they were not knowing it, but they knew that we need to use a sharp tool to cut something. And lathe is one of the oldest machines, and it is called as the mother of all machine tools. So thus manufacturing started there, and then quickly it progressed to a level so where we are able to produce the components without the intervention of human beings. When we look at what are the things which have contributed for this kind of revolution, so now we call them as industrial revolution. So wherein in 1700s, so the steam engine which was invented, so that has contributed for mechanization of the machines. Mechanization means so what the human hand was doing, or the animal power or human power was doing, so it has been started being done by the steam power. So that's the first revolution has started. So then if you look at the invention of the electricity IC chips. These are all contributed actually for the development of industries. Then in 1900s, actually, the industry started streamlining itself, and then the production demand has increased a lot. So now if you look at the quantum of number of cell phones which are required, or automobiles which need to be manufactured, so they run into millions. And to meet that kind of requirements, so the traditional technology was not sufficient. So people have gone for several technologies, and one of them is the CNC machining technology. So in 1950s, after the Second World War, so 1960s, if you see, so the computer, the numerical controls, and then the computer numerical controls have been introduced, and then we started producing the components at a very high speed and with accuracy, with high accuracy and good surface finish. So thus nowadays, if you look at the types of machining centers, so you have something like even 21 axis control machines, and then the sizes vary from very small machines to a very huge machine tools. And if you look at the range of components which have been manufactured, and then the surface finish which has been achieved, so it's really amazing. You can see the parts. Now we have what is called as a high speed machining technology. So by means of which, right by machining itself, we'll be able to achieve the finish. So what we are seeing here. So earlier what we used to do is like we do turning, then go for grinding, and then go for super finishing operations to achieve high good surface finish. But nowadays we can do that with the high speed machining technology. And also if you look at the complexity of these components, so they vary from small sizes to a very complicated components. But then nowadays we have the technology to produce the components. So now if you look at the components which have been machined, so we have what is called as the freeform surfaces, so where they doesn't follow the standard curves like a circle, ellipse or other curves, but the shape actually varies with freeform. So we used to call them as splines. So, but nowadays we have the control, what is called as the NURBS, non-uniform rational B-spline curves. So with that, we'll be able to control the geometry very accurately, and we have the machine tools by using which we'll be able to manufacture these kind of complex and freeform shapes. So this is another example. So how complex the components can get. And jet engine is one of the most amazing product which has been manufactured in the modern history by the human beings. So the components are very complex, and the reliabilities which are required are very, very high. So many times we wonder how reliable they are. When an aircraft accident happens, it becomes a world news. But if you look at the number of people who are dying by the accident caused by the aircrafts to the road accidents, the accident caused by the flights are minimum, and the people dying on the roads are very high. So thus the reliability has been built into such kind of a complex system. So this is another example how huge and the complex the systems can become. As I said, high-speed machining is one of those technologies which have contributed for producing the components with a very good surface finish. And usually the RPM, the rotational speed of the machine tools is more than 20,000. So in some places they say 18,000 RPM, or it can be even more than 20, 25. And nowadays, we have very, very high speed machine tools where the spindle RPM can range up to 2 lakhs and more. So this is the way how when we do the high speed machining, so we'll be able to get the components with a very good surface finish. So there are several examples which we can show how we'll be able to machine these kind of components. Another interesting technology which has come up recently is called as diamond turning. So if you look at the mirrors which are being used in the space applications, so they need very high reflectivity. But at the same time, like if you look at the mirrors which you have been using in our bathrooms and the domestic purpose, you cannot use them in the space because the temperatures vary from plus or minus 180 or plus or minus 200 degrees centigrade. So when they are exposed to the sun, it will be plus 180 to 200 and above. And when there is no sunlight, so it goes down to minus 180, minus 200 degrees centigrade. So how do you make the mirrors to work in this kind of an harsh environment? So we need metallic mirrors. And there to produce these metallic mirrors, so we have been using the technology called as diamond turning. So where the diamond is used as the tool. You may say, fine, why not? We can just on any machine, we can put a diamond and then machine. No. Though diamond is the hardest material, but it is very, very sensitive to vibration. So if you use a diamond tool and then put it on an ordinary lathe machine, and if you start turning, within no time, it will break. So thus, we have actually technology to make the vibrations almost close to zero and then to control the tool very accurately. So when you do that, so we can get the surfaces with such kind of an reflectivity. So something around 99.999%. So in India, we have such kind of a facilities. So where we are able to produce both the flat mirrors and the spherical and even aspherical mirrors. So by using this diamond technology. And also we have huge machines which are able to carry out the multitask. So as we said, we'll be taking you to the laboratory visits and also to the research part. So where we have the AMTDC, so wherein this machine is located, you can go and have a look at it. So you name any machining process, so this machine will be able to do it. And you can see the size. When a person is standing here about 6 feet, so this is the huge size. So thus CNC machines have developed to such an extent, so where we are able to have such a huge machines which will be able to carry out almost every operation which is required for a complex and huge component. That is on one side. But interestingly, on the other side of it, we have what is called as micro and nano technology. So where we want to produce the components of a very, very small size. So Richard Feynman, he gave a statement long back like 1959 telling that there is plenty of room at the bottom. That means below 1 millimeter, there is plenty of space. But then people thought it may not be possible to make the components like that. So they also said, like, why cannot we write entire 24 volumes of Encyclopedia Britannica on the head of a pin? So at that time, it looked impossible. But nowadays, it's almost very close where we are able to make that possible. And also now when we look at our gadgets which we have been using every day. So the cell phone, for example. So earlier when the technology came, the size of the cell phone was very huge. But later, now it has been made to such an extent that it is just we'll be able to carry it in our hand and we can take it wherever we need. And similarly, the size of the computers. So it was a big hall size and weighing several tons. But now we can actually make those computers just where we can hold them on hand. And also, if you look at the size when we were doing our PhD, myself at IIT Madras, so we were measuring the memory and other things just in terms of KBs and at the most MBs. And then the size of these computers were very huge. But nowadays, even the small cell phones have much, much higher memory and the computational power when compared to those huge machines. Here are some of the examples, like a mini petrol engine and then cameras. I think these days cameras are coming in tiny sizes of order, whatever the order you can mention. So they're very, very small. So they can be kept even on a pen or in any component. We'll be able to introduce these kind of cameras. And also, when you look at the machines, usually we think that they are big and huge, but it is not so. So we can actually make the machines so which can even, we can hold it right in the palm of our hand. So these type of machines were even made decades ago. And nowadays we are able to produce very high speed machines with a smaller sizes. So this is one of the micro machine tool which we have developed in our lab. So when you are visiting, you can look at that. So the spindle RPM is 1 lakh RPM. And we use the tools which are of the order of 200, 100, and even we have the tools which are below 100 micrometers. You can imagine 100 micrometers. That means our hair diameter is of that order, and we have the tools, mechanical tools. So by using which we can cut even the metals, we can drill the holes, make the channels by using such type of tools. So when you visit, you please visit this facility and also look at the tools. And if you keep them under the microscope, you can see actually how the profile of these tools have been made. So they maintain actually the exact angles here, and also the profile, helical profiles even in these small tools. So sometimes the microscopes are not able to magnify it enough. So we have to take the SEM images. So we have taken several SEM images of the micro tools, and you can have a look at the tools and also even the images. And also we have an ultra high precision, high speed micro machining center. So it is located in the ground floor in the Ranganathan building. So students will take you there. And can you imagine the spindle speed is 1,60,000 RPM. And also the specialty is it is vector controlled. That means when the tool is rotating, so every angular position of it will be noted by the machine controller. It's actually a German make, and then the controller is Heidenheim. So even when the spindle is rotating at such an high speed, 1,60,000 RPM, so every angular position of it is being noted. So that is the way how the machines tools are made today. And even here we can mount the tools up to the order of like 30 micrometers, 40 micrometers, and then we can do the machining of not only like non-metals but also the metals. Actually, when we were purchasing this Kern machine tool, so the manager of the company, he has come and then brought an interesting sample. So they took the hair of the secretary of that Kern machine tool company, and then they drilled a hole of about 30 micrometers. So the hair of the European woman was about 60 micrometers. They drilled 30 micrometer and then inserted a copper EDM wire, electrical discharge machining. We use the wire and then they inserted into it to prove that. So they have made a through hole. And then they took the SEM image, and he also actually brought even the sample with the SEM image. So you may ask, what is this sample to do? But here there is a technology, because like if we cannot drill a hole in the hair by using lasers, because it is going to burn. And then you cannot use electrical discharge machining because hair is not a conductor. But by using the mechanical tools of this order, 30 micrometers, so they were able to drill a hole. So it's an amazing thing. So we have been using this machine for several such kind of an applications. Then with all these technologies, now we have moved into what is called as a nano manufacturing, nanotechnology, and even a micro or a nano factories. So wherein within a small size, we'll be able to incorporate all the machines which are required and then make them compact. And there are concepts wherein we can even carry the whole factory with us. It is called as portable factories. So where you can carry the factory with us. So that is the way how the technologies have developed. The other interesting technologies which we are looking at, and even this course will be concentrating, will be the laser-based technologies. So we have a center which is called as Center of Excellence for Advanced Laser Material Processing and Surface Engineering, as Professor Sushanta has mentioned. So here we have been looking at the applications of different types of lasers for various processes. And then we'll be looking at the applications of them. So if you look at the laser, so basically we can divide them into different categories, but for our sake, so I have made them into 3 categories, like continuous lasers. Then we have what is called as the pulsed lasers. So where we don't send the laser continuously, but send them in pulses. So then that becomes a pulsed laser. We can have microsecond lasers, nanosecond lasers, then picosecond lasers, femtosecond lasers. So what is the speciality of these pulsed lasers is that we send the laser pulse in the time order of like 10 to the power of -3 or -6, -9, -12 or -15. So when it is -15, we call them as the femtosecond. So -9 nanosecond. So picosecond 10 to the power of -12. So when you are sending these pulses in that short period, so we have something wonderful which will be happening here. I'll just show this one because it is interesting. So when you put these pulses here, the top layer, so where generally there will be free electrons, because we are talking about machining of the metals. So these free electrons will absorb the energy. So it will be generally in the order of 10 picoseconds. So it will absorb. Then once they absorb, they get heated up, and before even much of the heat being passed to the bulk of the material, they vaporize. That is called as laser ablation. So it's not even melting, but directly from solid, it goes into the vapor state. So it gets ablated. So thus the material will be ablated and will be removed. And thus it is very interesting that if you cut a material by using continuous lasers, you find that the part gets heated. You cannot touch them. But if you use the femtosecond laser and then cut, so immediately after machining, you can touch them and the heat would not have even passed to the bulk of the material. Actually, one of our PhD scholar, he has worked on modeling of this. It's a very, very complex because we are talking of the order of 10 to the power of minus seconds in time level. And if you look at the amount of material which is removed in that for one pulse is about few nanometers. So on one side, we have smaller size. On the other side, you have shorter time. So thus the process was very, very complicated, but we have actually put the single pulses on the titanium material and we have studied how much material is removed when you put one such kind of a pulse. And this is the SEM image to get even the maximum size of that. So we have to actually grind the workpiece and then later it will be hand ground and we could actually get the maximum section because we couldn't find any instrument literally to make the light to go into that and then measure the depth of the hole and the material which has been removed in that short period. Okay, I'll just go back to the slide what I've been talking about. So thus, when you put the lasers with the different wavelengths on the material, so the materials behave differently. So it is called as laser material interaction, laser matter interaction. And that is another interesting topic, so where we can work. So there are several machining processes which we can carry out by using the lasers. So we can machine them, we can mill the surface, we can get different shapes, and we can produce even complicated shapes by using the laser machining processes. And this is one of the interesting setups which we have developed for machining of the coolant holes in turbine blades. So you can visit this facility. So here what we have done is hybrid, means we have combined two processes so that the making the holes will be more efficient. So what is the problem here is, as I said, femtosecond lasers, when you focus, they are something like the doctor's scalpel. That means the knife which the doctor uses. So even to cut the eye, so they cut just a layer. That means very fine cut. So the femtosecond lasers will do that. Now, when you cut a hole, if you want to cut a hole by using the femtosecond laser, it takes long time because it's a very, very precise. But then in an industry, when you want to put hundreds of holes and even thousands of holes for a turbine, so the material removal rate is not sufficient. But then on the other hand, we have the EDM process. So in this case, it is a micro EDM, so which has a much better material removal rate, MRR, we call it. So thus, what we have done is we initially make a hole by using the electrical discharge machining. Then we finish the hole by using the femtosecond laser. So thus, we get higher material removal rate, and at the same time, we can get a very precise, accurate holes. So this I have already talked. And if you look at the way how the EDM works, micro EDM, electrical discharge machining, so it is a very, very small diameter. And if we introduce the tool straight away into the workpiece, the tool, it's just a rod, it's going to break because there will be debris and then when it goes inside, it gets stuck and then breaks. So for that, what we have done is, it's called as a peg drilling cycle. So if you want to drill like 1 millimeter hole, so first make a small, maybe fraction of a millimeter. So then once the hole is done, take the tool back so that the debris which is there can be removed. It's called as a dielectric. It will be flowing and then it removes. So then again go down more further, then come back, retrieve, then go. So this is called as a pecking cycle, like a birds when they peck the grains. So that is the way how they do it. So it is called as a pecking cycle. So we'll be able to drill the small holes. So then later we finish it by using the lasers. Okay, here another interesting concept which happens when you are using different types of lasers. So this is a nanosecond laser. So you can also visit this facility. So here the pulses will be sent with a period of nanosecond, and then with a high energy. So then what is going to happen is that we are using it for what is called as a laser shock peening. So we take the workpiece, put it in a media like water or other media, then put the laser pulse on that. So the laser pulse will create a shock wave, and then that wave travels. So I think you might be familiar with what is called as residual stresses. So which will be there when you machine a component, there'll be residual stresses in that. And if you use that component with residual stresses, so the life of the component actually decreases. So one of the application of this one is the landing gear of an aircraft. So usually when the aircraft lands on the wheels, so we have a landing gear, and it takes a lot of load in a fraction of a second, kind of an impact load, and that cycle actually repeats. So if there is any residual stresses in the landing gear, so the components actually fail. We need to remove the residual stresses in that. So that is what we do by sending these shock waves. So we'll be able to actually relieve those residual stresses which are there in the component. So this is the laser which we have been using for carrying out this operation, which is called as laser shock peening. So then we are actually using the continuous lasers for 3D printing. So we have the laser, even this facility in the lab, so where you can look at it. So we use the powders or the wire for carrying out the 3D printing. So nowadays, the 3D printing has become a very important manufacturing process. All this time we have been talking about what is called as subtractive manufacturing. So you want to make a component, so you machine and remove the material which is not necessary and then use the component. So that is subtractive process. But then the thought process came, why do we need to remove the material and waste? Instead, if we can build where we need, so that is more efficient. So that is the way how the 3D printing technologies have come. And then we use the laser power actually to melt the either powder or the wire based on what is the type of process which we are doing, and then it will be printing. So you can also have a look at this machine. So this machine actually we have designed and then made with the help of a vendor right in Chennai. And this is a multi-purpose. So we can print with 2 different types of powders and we can control their composition. So this head, when we change, we can actually use it for even cutting or laser cladding. Cladding means it's a huge, large thickness of the material deposited over a soft core material. And also we can do on the cylindrical part. So we have a rotary head here. We can put the component and carry out the laser cladding on the axisymmetric components. So these are some of the components which we have made by using the powders and also the wire. So it will be called as directed energy deposition. So that energy is supplied by the laser. Actually, it is an interesting fact actually to observe. So what kind of melting process which will take place when you are going to focus the laser on the powder or the wire. So for that, what we have done is, you can see here, so we have put an IR camera, infrared thermal camera, so which will be able to see the temperature. So in the video, you can notice here. So when the wire is here and when the laser is focused on that, it melts, and we call that as a melt pool. So I've been trying to understand how that melt pool is there, what are the temperatures, and what is its effects on the quality of the component which is produced when you have a different temperature, different rates at which you move the laser and all these things. So we have been investigating. So you can have a look at that. So that's additive manufacturing, as I have said. It's also called as layered manufacturing. So by using these type of machines, so we'll be able to work on the metals. So most of the 3D printers, if you see, so they're all non-metals, and mostly dealing with metals is very complicated because you need higher energy levels, and controlling that is a complex process. But we have been looking at this process. And why the additive manufacturing process is very important, because we can produce the functional components. So now, for example, like you have a machine, and then if a component fails, I think they always take an example of a turbine blade component. So even when one blade fails, the whole component need to be removed. We have to replace them, and that is an expensive. The materials which are used are titanium, nickel, and single crystal type of materials, which are very, very expensive. So what we can do now is, we can make a component, fit them, or we can even use these type of 3D printing technologies, additive manufacturing technologies, for repairing the components. And I think recently we have been hearing, and Professor Satyan is also working on printing of these materials in the extraterrestrial materials. So wherein in the space, you can't carry a building from here, but use the materials in the space, whatever are available, and then print what we need. So that is the way. Like, for example, now today you are coming to the hostel and you may not have a bucket or a mug. So instead of carrying them, you print what size you want, what you need. Probably after a few days, these things will become a reality. Okay. So any questions? So we have another 17 minutes. So if you have any questions, you can quickly ask so that I can know, I can understand whether you are able to follow or not. Do you have any question, participant? Okay.
Sir, can you just briefly explain about the femtosecond laser concept? I didn't get it much.
Oh, okay. So what we are going to do is, what I am giving all these things are just an introduction to give you a overview. But I have a lecture on, let me look at the date. So we are going to talk about the laser material processing, how actually it takes place. So I'll have a 1.5 hour lecture on that. So here I'm just giving the brief introduction of this process.
Anyone else having any
Any
doubts?
Yeah. So it will be on Wednesday morning at 8:30. Laser assisted surface texturing and its applications. Sorry, on Tuesday. It's on Tuesday. Femtosecond laser micro machining and applications. So in that I'll give you more details. Yeah. So if you don't have questions, I'll quickly move on. The application of artificial intelligence technologies have radically changed the way how things were made. So earlier, when you talk about artificial intelligence, we thought it is for computer science and other circuit branches, but no. Now I'm going to show you an example how we have used these artificial intelligence technologies for manufacturing. So we have actually have a factory called autonomous factory, even that you'll be visiting. So where we have applied the artificial intelligence techniques to the mechanical machines, and then they become intelligent, and actually they can even take the decision to carry out the production. So I'll also be giving the details of this on Friday. So we'll be talking about application of AI for monitoring and control of autonomous factory. So thus, these artificial intelligence techniques, when they're combined for the mechanical or manufacturing processes, so the way how the things have changed, I'll be talking to you in detail. So what is this artificial intelligence? So it refers to the simulation of human intelligence by using the machines. So thus the machines can carry out the task like what the human beings does. And nowadays probably you would have heard these terms like machine learning, deep learning, AI kind of a techniques. So wherein by using them, we can make the machine more intelligent than what it was created. So usually we used to say that the computers and these machines will be as intelligent as the creator, or whatever the knowledge we give, only that much. But nowadays it is not that. The machines can learn through experience and they update their knowledge base and they can even become more intelligent. And also we have convolutional neural networks wherein you'll be able to have a lot of hidden layers by using which you'll be able to have a knowledge processing and decision making like as intelligent as human beings or even more. Another interesting concept which has come up is what is called as a digital twin. So probably you'd have heard about twins. Okay. But here we have a digital twin. So wherein we can make the replica of a physical system digitally. So we have a physical system and we can actually make a digital system. So that is called as a digital twin. So the way how the physical system behaves, so the same thing, the digital system also will behave. And then we can actually simulate a process or a system behavior in the digital world. And then we can send those commands to the physical system so that we'll be able to achieve the goal. So in the digital world, you can carry out several trials. And then finally, once you have optimized your process so that you can send it to the physical world and achieve the required goals in the first attempt itself. So there are details about these digital twins. So where you can have the digital twins at a system level or at a process level or even at a product level. So these things are also I'll be talking in detail on your Friday. And there are several applications. So where you can apply now from biology to chemistry to every area, to engineering, everywhere. So they have been applying the digital twins, and we have applications in the real world. And finally, I want to talk about the metrology and measurement techniques. So many times in the manufacturing, we talk about all the processes and everything, but forget about the measurements. And the importance of the measurement is very, very crucial in making the parts. So actually this term, I don't know if you are familiar with metrology. Metrology means it is science of measurement. So metrology is nothing but the science of measurement. So it is very, very important because here Lord Kelvin, so he made a statement telling that when you can measure what you are speaking about and express it in terms of numbers, you know something about it. But when you cannot measure it, you cannot express it in numbers, your knowledge is of meager and unsatisfactory kind. So to put this complicated statement into simple words, so what he was trying to tell is that if you can't measure, you can't make it. If you can't measure, you can't make it. So that means all the processes what we are talking about, so if you can't measure, you'll not be able to make. Why that is true? For example, I told about micro machining. So think that I made a micro hole of 10 micrometers and I am claiming that this is 10 micrometers. But how do you prove it? If you don't have any technology to measure and say that, okay, it is at least 10.1 micrometers or 10.5 or even 9.99, if you can't say that, I can't prove that I have produced a hole of this size. So thus, if you can't measure it, you cannot produce it. So metrology is very, very important. So please visit this lab which is there in the basement of the building where you are there. It's MSB, Mechanical Sciences block. You are on the 3rd floor, but in the basement, ground floor and just below level. So you can find this instrument. One of the most popular instruments which are being used for measurements these days on the shop floor is the CMM. CMM is nothing but coordinate measuring machine. So with the technology of just getting the coordinates of the component, so the remaining calculations are done by the software. For example, if you want to measure the length, you touch at 2 points, so it gives the XYZ components, then you fit a straight line, and or you can use the distance formula and get the distance between them. So thus CMM is a very, very powerful tool. It is a comprehensive tool which will be able to make several measurements. Earlier, like if I want to measure angle, we'll have one device. If you want to measure the length, one device. But now by using CMM, you can carry out all these measurements in one single machine. And also, this CMM has a multi-sensor technology. So what is this multi-sensor technology is that usually the CMMs will have a contact probe and then they make the measurement. And then this contact probe will be replaced by a non-contact measuring probe, so which you see on the right side, and then they carry out the measurements. But that will not be efficient. But here what we can do is both the signals from the contact sensor and the camera, which is a non-contact sensor, we can actually combine. You may ask, what is the use? Now, for example, if I have a component, big component, and then I have a micro holes in that. If I have only contact, I can measure these dimensions, but my probe cannot go inside, so I cannot measure the diameter. Then, if I take only the non-contact, so some of these measurements I'll not be able to get accurately. But now what we do is, if you want the outside dimensions, we can touch with the touch probe, and the micro holes, I can see it with the non-contact camera and then measure. And the software here has a facility. It combines both the data and finally gives me what is the dimensions of the component and where exactly this micro hole is located and what are the dimensions of that micro hole. So that is the way how the instruments are now, which are sophisticated, and you'll be able to use them for multi-purpose measurements. Another interesting measurement technology which we have used and which has come is called as computed tomography. You might have heard about CT scans for biological, like our organs, internal organs, they do it. But now we can use this technology for making the measurements in the solid material without cutting them. So, or without non-destructive testing, rather to say. So that is possible. Actually, some of the turbine blades and holes, we also actually use this CT for making the measurement. So this facility is there in the design section of, we have a NDT section there. We have not planned the visit, but if any of you are really interested, you can go there. There'll be two heads, micro CT and ordinary CT. So depending on the type of hole, the size of the hole which you are measuring, so we can change the heads and then we can inspect. So this is called as a CT, computed tomography, micro CT. That is a micro one. Other one is ordinary CT, computed tomography. So, and also we have several types of scanners which are being used. So nowadays, if you want to measure even very huge kind of a components, so the scanners are handheld, or it can be even mounted on the drones, and we'll be able to make the measurements on large components. And even we have been going one step ahead. We can even carry out the inspection virtually. So we can actually check the sizes of the component, the surface finish of the components virtually by the components which have been made in the virtual world. So you may not have a physical component, but virtual machining you can do and make the component, and then we can carry out the inspection. So thus we have several technologies. I think I have just limited to the facilities and the research what we have been carrying out, and I have told these examples. So thus, as I said in the beginning, initially manufacturing means making with hand. But nowadays, with the help of all the industrial revolutions which have happened, so Industrial Revolution 1, mechanization, steam power, and power weaving looms. Then Industry 2.0, so the mass production, and then the electrical power which contributed to that. Then Industry 3.0, automation and the introduction of the computers. And then Industry 4.0, we talk about what is called as cyber physical system, Internet of Things, and IIoT means Industrial Internet of Things. And now we have been moving into what is called as Industry 5.0, where we talk about autonomous factories, and we can carry out the whole of this process without the intervention of human beings. So the video on the left actually shows the mass production. So Industry 2.0. So where the Ford, they were making the cars. So you can see the assembly lines how they're making. But on the right side, you can see how the work can be carried out virtually. And then later, the same thing can be done by the physical system. So both the computer environment and the physical environment can interact with each other and carry out the task. So these are the developments which have happened over years, and we stand here today. Thank you very much for your attention. So we have time for 2 minutes. So we have any quick questions you can ask.
Sir, I have one question.
Yeah.
With the X-ray microcity facility, can we map the porosity of a metal part and then reconstruct to get a virtual object like a CAD design so that simulation can be performed later? Is it possible, sir?
Yeah. Yeah, it is possible. Actually, how the CT scan works is that it takes the scan layer by layer. Okay. So it takes. So then if you take one image, so we have actually taken the micro holes. So what will happen is in a plane, there'll be a hole and its size we can see. So then it moves by the fraction, whatever you say, few micrometers, takes another section. So if you imagine if it is a cone, so the diameter would have decreased. Then you move above, again smaller one. So it can actually, we have the geometric software, so where we'll be able to rebuild them and you can see the 3D. So that's what actually, when they scan our brain, doctors and all, what they do is, they will be done layer by layer and sometimes at a different angle. So it combines all the images and finally gives the like a real solid. So you can work on that. Nowadays, even we are using those CT scanned images for 3D printing. If there is a bone fracture or something, so they take the CD scans, so the geometry will be reconstructed, then given for the 3D printing, it will slice and STL files it will create, and finally we can 3D print it. So obviously simulation you can do.
Thank you, sir.
Any other questions?
Okay, I think we have one more question.
Good morning, sir.
Yeah.
I have one question regarding composite material. So, is there any, if suppose if I create a gear in composite layer by layer, so can I cut using the laser technique? Can I cut that that materials based on the gear?
Yeah. See, actually, these lasers are so powerful. Literally, any material you can ablate. That means you can vaporize. So we are cutting like titanium, nickel based alloys, and we are also trying to experiment on the single crystal, which are very, very hard materials. So these alloys are called as a super alloys. And if they can cut that, obviously composite materials, we can do it. So metal matrix composites are also have that equal kind of a strength. So that also we can do.
Is it possible in the fiber composite?
Yeah, obvious. It's that energy what you get is too high for fiber composites. So that is very soft material rather.
Yeah. Thank you, sir.
Thanks.